Hi students, in this lecture we are going to learn electric field. So first understand what is it. So earlier we have learned Coulomb's law, and in that we have discussed between two point charges force of attraction or force of repulsion and how to calculate that force, right? And in that if you observe, even though there is no physical contact between the charges, suppose taking q1 q2 at some separation, even though there is no physical contact, a charge is exerting force on other charge. So to explain this force, we are taking now field concept. We are taking field concept. So what we are saying is, if we consider any charge, I am taking here a charge q. It can be a point charge or it may not be a point charge, or you can say charged body. So whenever we are taking a charge, it produces electric field in the surrounding space. I am repeating. If you are taking any charge, that produces electric field in the surrounding space. Or you can say in a simple language, it is having its influence. It is having its influence in its surrounding space up to a certain range. And that influence region what we call electric field. Okay. So charge is producing electric field in the surrounding space. If any other charge comes into that region, suppose it is now Q naught. If any charge comes into that region, then that electric field exert force on that charge. That electric field exert force on that charge. So here step 1 is charge is producing electric field. Step 2 is that field exerting force on that charge. Now, if you observe, if both are same sign, let us say both are positive, then this is now repelling this charge. Force will be right side, right? Suppose I am placing now this charge somewhere here. Now repulsion will be like this along this line, right? So direction of force depends on the position of the charge. Direction of force depends on position of the charge. At the same time, what is the distance of that charge from this charge? That means at a point, force acting on a charge depends on distance of that charge from the other charge and location of that charge. So like this from point to point, magnitude of force changes as well as direction change. So to know this one, we are defining one vector quantity, and that vector quantity is known as intensity of electric field. It is intensity of electric field. Notation is E bar. So E bar equal to, see how it is defined, limit Q naught tends to 0. It is F bar by Q naught. So first understand what is the meaning of this. So here we have taken one special case like field due to one charge. Okay. But remember that field can be due to any number of charges. It can be due to any number of charges. Let us take here. Let us consider here. So I'm taking here one space. This is one space. In this space, electric field is present. And who is now creating this electric field? It can be a point charge or it can be combination of many charges. So which is not required for us. So simply there is electric field in this space, in this entire space. And at one point, we want to know strength of that field. We want to know strength of that field. Then there we have to imagine one point charge. It is a positive charge and one point charge. It is a Q naught. I am repeating. In this region, there is electric field, and that field can be due to one point charge or it can be due to combination of many charges. So which is not required for us. But what we want is at a point, what is now strength of that field? At the same time, direction of field. Okay. For that, we are imagining one charge. It is a positive charge. Let us say Q naught, where we want to know strength of the field and direction of field. Right. Now, force acting on this charge that is given by, or you can take the definition part here. Force acting on that charge, that is F bar. Okay. Force acting on that charge is F bar. Divide that force with a Q naught. That is giving us strength of field at that point. That is giving us strength of the field at that point. Now here we have to focus on Y condition limit Q naught tends to 0. Y condition limit Q naught tends to 0. So we are saying here electric field is present in this space and we want to know strength of that field at this point, right? So when we are placing a charge in that field, this charge is also going to produce electric field in the surrounding space. That means this is going to disturb the existing electric field. I am repeating, this is going to disturb the existing electric field. But our intention is to know strength of the existing electric field. For that purpose, we are taking this charge must be very small. So when it is very small, its presence cannot change the existent electric field. That means we can get a strength of the existing field accurately. That is the purpose why we are taking very small charge. Okay. So strength of electric field is defined as limit Q naught tends to 0 F bar by Q naught. So in words, it is a force experienced by a unit positive charge placed at that point, because when this is equal to plus 1, E bar equal to F bar, right? So that is a way we are giving in sentence. And why we have taken very small means this charge should not disturb the existing electric field, right? Okay. And once we have the value of E bar at a point, once we know the value of E bar at one point, then if we place a charge at that point, then force acting on that charge is given by F bar equal to Q into E bar. See, in this what we have taken, E bar is already known. It is already known at a point where charge Q is placed. Then force acting on that charge is given by Q into E bar. It is just like F bar equal to M into G bar, gravitational force, right? So with the help of this vector, we are knowing strength of the field at each and every point and direction of field. Okay. So this is the way we are defining strength of electric field, right? See here definition part how it is given. So it is the electric force experienced by a unit positive charge placed at that point. So limit Q naught tends to 0 F bar by Q naught. Okay. Let us now focus how to calculate electric field in some special cases. Like, see, first one, electric field due to a uniformly charged thin wire. We are taking a uniformly charged thin wire. Okay. Right. See how we calculate. So condition is given. It is a uniformly charged thin wire. Uniformly charged thin wire. Just a minute. Right. We have taken a thin wire here, which is uniformly charged. Let us take charges Q on this one. And we want to find out strength of the field at a distance R. Distances are from the wire. And let us take the ends joining the wire. The ends joining the wire, making some angles with the normal drawn to that wire. Let us take those angles are alpha and beta. Okay. So the ends joining, making angles alpha and beta with the normal drawn. Okay, distances are. So in terms of Q, R, alpha, beta, we have to find strength of the field at this point. So in that, see how we are starting the problem. So just now we got one condition, that is F bar equal to Q into E bar, right? So F bar equal to E bar if Q is plus 1. Okay. We can find force by using Coulomb's law here. So whenever we want to calculate strength of the field, first imagine a unit positive charge at that point. So step 1. So whenever we are calculating strength of electric field, first we have to imagine a unit positive charge at that point. Y means if Q value plus 1, E bar is equal to F bar. Okay, right. So first of all, take here 1 unit positive charge plus 1. And if you want to apply Coulomb's law, we require one more point charge. But this is a line charge. So we require one more point charge. So here what I am doing is, let us consider take one more diagram. Right. Now consider from this normal at some distance. Let us take at some distance x from here, at some distances, element of length dx. It's a length how much dx. Now this becomes a point charge because dx is very small. Now because of this point charge, force acting on this unit positive charge. See carefully. We want to use now Coulomb's law for these 2 point charges. Suppose this angle is now, take it as theta. Okay. Now force acting by this positive charge on this positive charge. Okay. Suppose take q value is positive. Okay. No? Right. Then this will repel this point charge. It is now along that line. Okay. That is now df bar. You can say df bar, or I can take it as d bar because e bar equal to f bar. Okay. So this I am taking as d bar. Okay. Let us take now for these two components. For this take two components. One is normal to that wire. Other one is parallel to the wire. This is a theta. This also theta. So this becomes now dE cos theta, and this becomes now dE sin theta, right? And the value of dE how much? It is now, I am taking in the place of 1 by 4 pi epsilon naught. It is a K. Q1, one is a positive charge plus Q, so plus 1. Other one, take it as it is now dq. Okay. What is it? It is dq, small charge dq. So k into q1 q2 by r square. Distance how much? This is now r, right? This is x. Then distance between those two charges is r square plus x square under root. So taking it is now r square. That means it is r square plus x square. That is now modulus value. Okay. This is now modulus value. So modulus of E bar equal to K into Q1 Q2 by R square plus X square modulus value. So we want to calculate now these two components. One is normal to wire, other one is parallel to wire. Okay. Now see carefully. If you observe in this one number of variables, R is a constant, X is variable, and here theta also variable, right? So we have to convert this into single variable. Okay. Na? So I'm writing here. I'm writing it is E parallel is equal to. So what do you mean by parallel? Component of E bar parallel to wire. Okay. That is now our first calculate normal to wire. Calculate normal to wire first. Right. We are calculating component of E bar, that is normal to wire. E normal, that is equal to integral dE cos theta. dE cos theta, that is equal to integral, it is a K into dq. dq means how much we can write here. dq means if length is L, that can be taken as q by L into dx. Okay, in the place of dq. Other one is 1, right? Dividing with r square plus x square into cos theta. Okay. Now in this number of variables, x is variable, theta also variable. So we want to convert this into single variable. Okay. Then see, we want to connect now, means we want to convert into single variable by connecting R and X. You can see from diagram relation between X and R, that is given by that is given by tan equal to X by R, right? Tan equal to X by R. So X equal to R tan theta, R tan theta. We want in this one dx value. So for that, what I'm doing is I'm differentiating this. So differentiate this. So dx equal to R is a constant, derivative of a tan secant square theta d theta. Now substitute in the place of x. It is x squared r square tan square theta, right? So I'm taking r square outside. It becomes r square secant square theta, and this is now here dx r secant square theta d theta. So substituting this value, this becomes you can take a k q by L outside, integration of, I think here we are having r secant square theta. This is r square secant square theta, right? R square. This is now r outside. Remaining is now cos theta d theta. Now limits. While taking limits, we should be very careful. We can see with this normal, one is clockwise, alpha is clockwise, beta is anti-clockwise. Beta is anti-clockwise. So if we consider clockwise as negative, anti-clockwise a positive, then this is taken as minus alpha to beta. So here what we have taken, anti-clockwise as positive, right? That means now this becomes K Q by L, charge per unit length, that is linear charge density, notation is lambda, K lambda by R, it is integration of cos theta d theta, that is now sin theta. Then this is taken as, that is now sin beta minus sin minus alpha. That is now expression for normal component of the field. That means normal to the wire, right? Now coming to parallel component, then see what we get. Coming to a parallel component where change comes. This entire part as it is, only change in the place of a cos taken now sin. That means finally it is a sin, right? Integration of sin, that is minus cos. That means we are going to get here, k lambda by r, it is cos, see what we have done is a cos beta. I'm just writing difference, okay, not minus, difference, whichever is more. Cos beta difference cos alpha. We want only modulus value, okay? That's why taking the difference. So this is now parallel component and this is now a normal component, okay? Resultant of those two gives us intensity of electric field at that point, okay? And here one important point is direction of this field will be along the angular bisector. That means, I will explain here. Let us now consider one special case. Let us now consider one special case. That is, wire is large. It is a long, thin wire. Long in the sense it is infinitely long. See, then what happens? If you are taking infinitely long wire, this extends up to infinity, and this also extends up to infinity. Okay, and we want to calculate now field at this point. Okay, now if you observe line joining this point to this end of the wire, that will be 90, right? Because this is up to infinity. In the same way, line joining this point and to this end of the wire, and this also becomes infinity. I will take a different color to make it clear. So if you are taken now line joining this point to the one end of the wire, that makes angle 90, and here also this line makes angle 90. So total angle is now how much? 180. Okay, that means if this is a positive charge, since we imagine here unit positive charge, that will repel now this one. It is it is it is now like this. This is now direction of V bar, which is normal to this wire, and we can see total angle is now 90 plus 90, 180. This is along angular bisector. Okay, that means in this case C value how much? It is equal to, see, if you substitute here 90, sine 90 minus sine minus 90. So 1 minus minus 1. This is 2, right? That means it is now 2k lambda by r. This is the normal component. And coming to parallel component, it is 0. Because in this, so this is alpha, right? Alpha. Okay, not beta, alpha it is. So cos 90, difference cos 90. This comes out to be 0. That means when you take infinitely long wire at this point, what is now strength of the field? It is only normal to wire. Its value 2k lambda by r. What is it? 2k lambda by r. And coming to parallel component, it is 0. Okay. For example, we want to calculate now. We want to calculate now at one end of a infinitely long wire. Where is it? At one end of a infinitely long wire. I'll take a different color here. Right. Consider now infinitely long wire. Okay. This extends up to infinity. And we are taking a point now at one end of the wire. At one end of the wire. So taking infinitely long wire, we want to calculate strength of the field at one end, means close to one end of the wire. Then see here, coming to normal component. So here alpha, coming to alpha value. Alpha becomes 90. Beta becomes 0. Okay. Therefore, E normal becomes K lambda by R. Since we are taking this is a positive charge and this is unit positive charge, this will have one more component. It is now like this. This is E parallel. Okay. And this is also equal to, that is also equal to how much? K lambda by R. If you take now resultant, if you take now resultant, That will be along the angular bisector, that is E bar, okay? Because both have same magnitude, angle is 90 between them. So this is now along angular bisector. So whenever we are calculating strength of electric field, it will be means due to in uniformly charged thin wire. It is along its angular bisector. Okay. So we have to remember one is what is the normal component and what is a parallel component. Okay. Right. I hope you got a clarity.